Amylase is an enzyme that breaks down starch into sugar. It is present in the human saliva. Food that contains much starch but little sugar, such as rice and potatoes, will taste slightly sweet as they are chewed because amylase turns down the starch into sugar in the mouth. Amylase family of enzymes is of great significance due to its wide area of potential application, such as application in pharmaceutical and chemical sectors. High purity of amylase are required in this sector. Hence, it's very significant for us to develop an economic way, steps or process for purification to obtain amylase that yields maximum specific activity. Amylase are among the most important enzymes that are used in this present-day environment. These enzymes have been found useful in numerous applications, especially in commercial processes. Some examples of commercial processes include production of paper, production of brewing, baking, pharmaceutical drugs, and preparation of digestive aids, and many more. So in this video, we're going to discuss between two different methods of purification and characterization of amylase. And then we're going to compare, see which of these two methods will be a better method. So right now, we will look at the first method. Now we know all about amylase, but how do we actually purify and characterize them? So before we begin the purification process, we first need to filter the microorganism. In this step, Bacillus subtilis will first be grown in growth decay medium with the pH of the medium adjusted to 7 before autoclaving. Then 100 ml of the unicolor will be transferred into 900 ml of sterile starch raw medium and taken to be incubated at 35 degrees Celsius for 24 hours. After 24 hours of incubation, the cultured broth will be centrifuged at 0 degrees Celsius to remove the cells, and then the supernators will be taken to be used to determine the enzyme activity, while the pellets are used to quantify the total protein mass. Once the pellets are collected, they will be taken for an enzyme assay to determine the total protein content. Here, the activity of alpha amylase will be assayed by incubating 0.9 ml of enzyme with 1 ml of soluble starch prepared in 0.1 mol of phosphate buffer. After incubation at 50 degrees Celsius for 5 minutes, the reaction will stop, and the reducing sugar release will be determined by the addition of 1 ml of 3,5-methylsalicylic acid reagent with melters as standard. 1 unit of alpha amylase activity will be defined as the amount of enzymes which liberates 1 micromole of reducing sugar as melters per minute under the conditions of the assay. Total protein was determined by the Lowry's method with boron serum albumin as the standard.
Once those steps are done, the purification process of alpha amylase can now begin. There are 5 main steps in the purification process. Step 1. Ultrafiltration. Crude enzyme solution will be concentrated under the nitrogen stream by using the ultrafiltration membrane. The filtrate will be collected and reconcentrated under the ultrafiltration membrane, while the redentate will be collected for the further purification purpose. Step 2. Precipitation. The redentant collector will be added with solid ammonium sulfate with a constant stirring at 4 degrees Celsius to the enzyme to give a final concentration of 40% saturation. They are then kept for 18 hours at 4 degrees Celsius. Then, the precipitated protein will be separated by the centrifugation process and dissolved in 0.1 molar of phosphate buffer. Step 3. Dialysis. The enzyme solution will be dialysed in the same buffer for 18 hours at 4 degrees Celsius. Step 4. Gel filtration chromatography. The dialyzed alpha amylase sample will be applied into the Sepharos CF6B column and pre-equilibrate with 0.1 molar of phosphate buffer. The column will be washed with the buffer and the bound protein will be diluted by the same buffer. Precious will be collected and then assayed for the enzyme activity, which leads us to steps. Step 5. Step 5. Lyophilization and HPLC. The active fraction will show the extracellular alpha amylase activity will be pulled and concentrated by the lyophilization method and then be analyzed in HPLC for purity analysis. Once we are done with the purification steps, we are going to determine the molecular weight of the alpha amylase. Step 1. SDS page. The molecular weight of alpha amylase can be determined by comparing the electrophoretic mobility, that of standard protein with a known molecular weight. It will be taken into in situ electrophoresis. Step 2. Zymography, which is also known as in situ electrophoresis. After electrophoresis, the gel will be washed twice with the Tritox X100 to remove the gel. After washing of SDS, the gel will be incubated in 2% of starch solution buffer at 50 degrees Celsius and 20 minutes. The gel will be kept in the same buffer and stay with the iodine solution. Then the enzyme activity can be determined by the visible pale yellow band in the dark colored gel.
That we have looked at the method, it's time for us to look into the characterization of alpha amylase for the first method. In the characterization step, the quality of the amylase can be determined using different methods. Firstly is the effect of temperature. Extracellular alpha amylase activity was performed at different temperatures ranging from 25 degrees Celsius to 80 degrees Celsius. Secondly is the effect of substrate concentration. Starch concentration for optimum extracellular alpha amylase activity will be varied from 5 to 25 mg per milliliter in 0.1 potassium phosphate buffer with pH 7.5 to check for the enzyme activity. Kinetic data can be transformed into Lineweaver-Burk plots and the Km value can be calculated by slope of the curve. Thirdly will be the effect of pH and ionic strength on buffer. 0.05 molar glycine HCl acetate succinate with pH 6 to 6.5. Potassium phosphate, tries HCl and glycine NaOH buffer will be used to determine the optimum pH. Extracellular alpha amylase activity will be performed at 50 degrees Celsius for 5 minutes. Ionic strength of potassium phosphate buffer with pH 7.5 will be varied from 0.025 to 0.2 molar so that the extracellular amylase activity could be determined.
Right now we'll be looking into the second method, and the second method is actually beginning with getting a microorganism that produces amylase, where you will isolate this microorganism on an agar plate that contains 0.05% of starch, and this microorganism normally can be collected from garbage areas at the local site. Before we purify the amylase that we have collected previously, enzyme assaying and protein concentration need to be done. Amylase assay can be carried out in a condition of 55 degrees Celsius at 20 minutes and 40 microliter of reaction mixture. The reaction mixture normally contains roughly 5 microliter of the enzyme solution. The reducing sugar released by the starch is measured by using the NSA method at 540 nanometer, and glucose is normally used as a standard. 1 unit of enzyme activity is defined as the amount of enzyme required to produce 1 micromole under assay condition per glucose. Enzyme production can begin by inoculating 1% in a 300 ml optimized medium. Incubated at 37 degrees Celsius for 60 hours with 150 RPM. Samples will be taken at different times and checked for cell density by measuring the optical density at 600 nanometer and also the amylase activity. extracellular blood will be collected by centrifugation, and it's to be used as source of enzyme for purification. Hence, the purification of the enzyme in this method is also made up of 5 steps. Step 1. Ammonium sulfate precipitation. The enzyme will be precipitated from the supernatant with addition of solid ammonium sulfate up to 70% of saturation. All the subsequent steps will be carried out at 4 degrees Celsius under constant stirring and left for 30 minutes on ice. The precipitate protein will be collected by centrifugation at 4 degrees Celsius, dissolving the pellet in minimum volume of 10 micromolar citrate buffer pH 6. Step 2. Cephalix G50 chromatography. 2 milliliters of the enzyme from the above steps is to be loaded onto a Cephalix G50 column with a 50 micrometer citrate buffer pH 6. Fractions of 3.5 ml will be collected, and those having the specific activity more than 800 units per microgram in the void volume will be cooled and to be used for the next step. Step 3. DEAE cellulose chromatography. The enzyme obtained after the Cephalix G50 will be loaded onto an equilibrated DEAE cellulose column, pre-equilibrated with 100 micromolar of tris buffer at pH 9 at room temperature. The enzymes are emitted from the DEAE cellulose column by stepwise reduction of pH from 9 to 6 using 100 micromolar tris pH from 9 to 7 and 100 micromolar citrate buffer for pH 6. The fractions with specific activity more than 700 ml per microgram will be cooled and loaded onto insoluble cornstarch column. Step 4. Starch affinity chromatography. The enzyme obtained from the above steps are loaded onto an insoluble cornstarch column, pre-equilibrated with 50 micromolar citrate buffer pH 6. The column will be washed with cold water. Then the bond enzyme will be mediated by incubating with 50 micromolar of citrate buffer pH 6 and 25 degrees Celsius. Fractions with high amylase activity, which to say have more than 3,000 units per microgram, will be cooled and dialyzed with 3 micromolar of citrate buffer pH 6 and used for the next step. Step 5. Cephalchiral S400 chromatography. 2 milliliters of the enzyme from starch column will be loaded onto a Cephalchiral S400 column, pre-equilibrated with 50 micromolar citrate buffer at pH 6 in 200 micromolar sodium chloride. The enzyme will be eluted with 50 micromolar citrated buffer pH 6 in 200 micromolar sodium chloride. The fractions of 3.5 microliter will be collected, and it's checked for the enzyme activity as well as protein concentration.